no judging, no requirements. Judgment, no requirements. Where are my notes? I had them out. I was talking to you about them this morning. There they are. I was even proud of myself because I marked off where I left last time. So hopefully you've had an opportunity to tune in to the video this weekend and get caught up with any of the notes that you might have been behind on. Where we left off last week was exercise 15, which is on page 15, ironically enough. And we were getting ready to determine the pH of a weak base. Similar to determining the pH of a weak acid, we follow the same steps, but remember that X is going to be your OH ion, and when we take the negative log of that, it's going to give you POH and not pH. So when they ask you for pH and you calculate POH, all you have to do is subtract that value from 14, and you've got your answer. So just keep that in mind. The other thing that will occasionally happen is that they will sometimes give you Ka here, and you have to work with Kb. So remember, if they give you Ka, Kb would equal Kw, which is a constant at 25 degrees Celsius, divided by Ka, and then that'll get you to your Kb value. Does that make sense? Okay, so when we look at this one, if we are trying to figure out the pH for the solution of ammonia, this is ammonia, and when it interacts with water, it acts as a weak base. It's going to pick up one of the hydrogen ions, giving it, it's going to split the water and give us NH4+, plus what that leaves behind then is the OH. And that's what's leading to your basic condition within that solution. And this should have a double arrow because this is a weak base. What we have to do then is we set up our ice tables. Okay. Initially, we're at 15 molar. Nothing here, nothing here. When we go through this, we subtract X here and we add X here and here. So at equilibrium, we end up with X for each of these ions, and this ends up being 15 minus X. Our Kb is to an order of magnitude where this X here can be ignored. If we want to go back and apply that 100 rule, we could go back and do the math for that. But you can probably see that this is an order of magnitude greater than 100 times, right? Just from looking at the exponents. All right. So that means then that your Kb is going to equal X squared over 15. And again, we can disregard that X value. They gave us the Kb, so we can just plug that into here, multiply that by 15, and then take the square root, which will then lead us to an X value of
0.012.
Okay.
So did you say in the video that when all you have to do is just all you have to say is X is negligible in some writing somewhere?
Yep. Just have to denote that you have checked it out. You can see that this is an order of magnitude here. I believe it was like 10 to the negative 5 divided by 15. And then if that order of magnitude is either 0.001 or 100 times, 100 times one way or the other, then you could ignore it. Or maybe it was 15 over 10 to the negative 5. I'd have to look it up again. At any rate, that's going to be a big number. When we take this, then we end up with a POH. If I take the negative log of this value, I end up with a POH of 1.78. And then if I subtract that from 14, I end up with 12.2. Right? All right. So here is another one. We're going to calculate the pH. Methylalamine. Here we've been given a KB. See if you can plug and chug this information and come up with this for your value. I'm going to go take a tidbits. No, I'm looking at the wrong problem, guys. Really looking at the wrong problem. No, I did that. I had that right. All right, let's try it again. And I have 0.1 here. Why did I have 0.1? I'm looking at the wrong. I'm still looking at the wrong problem. Oops, if I flip the page over. Jeez. Okay, let's try it again. 0 to 1, which equals your hydroxide ion concentration. Your pOH then is going to equal 1.68, which will give you that for your pH. Sorry.
Okay, so I have a question for like the AP test. When we're doing, like if we're doing one of these for a short answer, do we have to show like all of our work?
You need to show at least, I mean, they're not going to make you put zeros down here and plus X here and plus X here. You could probably get by with some of that, but you need to show them initially, like your ICE table, you need to show them this stuff here, okay? Because sometimes they will actually give you credit for calculating some of these things along the way. And if you don't show work, they will give you absolutely no credit. If you just plunk that down for your answer, they won't give you, even if it's completely right, they won't give you any points at all. So no work, no credit is a very common thing that you'll see. And honestly, I haven't given you guys as many quizzes as I would have in a normal year, so you haven't experienced a lot of that more technical grading. But yeah, if you don't show them this, if you don't show them like your thinking here along the way, they won't give you credit.
Okay, because like, and the one thing I do is I don't usually do like the ice tables. I just kind of do the equations.
Yeah, I think if you showed them this, you'd probably still be okay. You do need to document somewhere that this part can be ignored though. So I don't know how you would do that without showing an ice table. But again, I think, you could probably even get rid of you could maybe get rid of the change line and show them this, not even write anything there and just write a C down here to document that that's happened, But I think you've got to give them something to show them that this can be ignored. But this is hypercritical that you show them this thinking here. That makes sense?
So, and then will X always be negligible on an acid base?
If it's not, then it would be something that you would be able to solve. They would have it set up somehow so that you could solve it without using the quadratic. So maybe they would tell you what the change is here. Like if they told you that this was 0.2 or something, then you would know what to subtract. You would know that that would be 0.8 there. Does that make sense? I don't know exactly how they would do that. I haven't seen a problem like that. Pretty much all of the ones that I see, you can ignore those. But they would tell you somehow. They're not going to make you use the quadratic, though. That we've been told. They've established that. Okay, so good with those? Making sense? All right. So acid-base properties of salts. So remember, a salt is any ionic compound that has a negative and a positive charge. Okay, it's not just sodium chloride. We have 3 categories of salts. We have neutral salts, we have basic salts, and we have acidic salts. Okay, now how do we know the difference between these? Well, a neutral salt is going to have an anion that would have originated, or you would have an anion that if you had hydrogen with that would make a strong acid. You would also have something with it, a cation. So your anion's here, your cation is here, and that would be part of a strong base. So like a potassium here. So if you have these 2 things come together, so we could have like potassium nitrate. That would be a neutral salt because your potassium would go together with hydroxide to make a strong acid, and your nitrate would go together with this to make a strong, this would make a strong base, this would make a strong acid. Does that make sense? Okay. So basic salts then come from an acid or from something where the material here is going to end up making a weak acid. Okay, so you could have like potassium acetate. Oh, that's what they used up here in the example. You could have strontium acid, yeah, because it kicks over. So lithium, sodium, potassium, calcium, strontium, barium. Any of those with an anion that would be a weak acid would do that. Yeah.
So if it's a salt that has hydroxide in the equation,
the salt wouldn't. No.
Salt wouldn't, but the equation that it comes from would have the hydroxide in it, doesn't it?
The equation that it comes from.
Like underneath, it's got the OH.
Well, what's going to happen is when this would be your weak salt. I mean, your basic salt, because what happens is that this will stay dissolved in water. It's not going to come together with the OH that's breaking up here. This, though, is going to go from here. It's going to meet up with a hydrogen. It's going to hydrolysize or split hydrogen. Hydrolysis, splitting of water. It's going to split a water, and this is going to form a weak acid. It leaves this behind. So that's going to increase the water. It's going to make the water basic because these are building up in there. Is that making sense? Okay. As opposed to acidic salt here. So here you've got your ammonium. Your ammonium then is going to take and it's going to split off one of these hydrogens. It's going to go over here, and this is going to be your weak base that's left behind then. So here we're building up the hydrogen ions in here, and that's going to increase or decrease actually our pH because it's going to make it more acidic. Okay, so if both the cation and the anion contribute to the pH, the situation you have to compare the Kas to the Kbs. If Kb is larger, then it's a basic. If it's smaller, then it would be an acid. So if you had something like NH4C2H3O2, okay, this would then be this situation. So there you would have to look at the Ka and Kb for these, and I don't know if they gave it to us. I don't see it listed here. I had those given in a chart up here, I think. Here we go. So Ka for this one, the Ka for that is 5.6 times 10 to the negative 10. That's the Ka though. The Kb would be a calculator. So if I want to know the Kb for that, that would be alpha W divided by 5.6 negative 10. So the Kb for that, for the NH4, would be 1.789 times 10 to the negative 5. Okay. The Ka for the acetate is here. That's 1.8 times 10 to the minus 5. So the Ka is bigger than the Kb for this one. So that means that it would be acidic salt. That makes sense? So look at the salt, ask yourself which salt and which base reacted to form it. Okay. Ask yourself, was it a weak or a strong? And embrace the fact that strong wins. Okay. So predict either the salt is acidic or basic based on that victory. And strong as a spectator, which means that it's not going to be part of it. And then you're going to look which one reacted, blah, blah, blah. We'll go through some examples here. Okay. I think it makes sense just to go through the examples. All right, so when I look at this, my Na, if that were to split water, what would it form? Well, the OH would go with that. This is a strong base, right? This right here then would go with the hydrogen to form, okay, that is a weak acid. How do we know it's a weak acid? Because it's not a strong acid. Okay. So when I form this, what's left over? Well, that's going to leave over this. Okay. So what will that cause the water to become? Basic. Okay. So that's going to be a basic salt. That makes sense? All right, so NH4 is the next one. See if you can figure out what's going to happen with this one. Kind of use this one as an explanation. Good. Were you able to get that this would be acidic? How about this one? Did you have time to do it? Good. Make sense? Any questions on those? All right, you ready? Ready not? Okay. So here we've got NaF in solution. The Ka value is given to us. We know when this goes into solution that the Na is going to go with what? What's that going to? The Na will form NaOH, which is a strong base. So we're not going to worry about that guy. We are going to look at this guy, though, because he is going to change things around. And we kind of were given a clue for this right here. Okay? So if we have our F ion and we take an H off of water, what's that going to leave behind in that water? It's going to form HF. And what else is going to be left behind? OH. Okay? So the OH minus then will contribute to this being a base, right? Okay, so we're forming OH.
Is those double arrows?
It should be, yes. Sorry. Anything that's not a strong acid should always be a double arrow. My apologies. Okay, so we are told that we're starting out with a molarity of NaF here of 0.3. This is H2O really here, before we hydrolyze it. So we're going to just kind of break that apart. We don't need to worry about its material as far as values. Okay, initially we don't have any of these. And we are going to subtract X here. We're going to add X here and here, which is going to give us X. And it's going to give us 0.3 minus X here. Now, they gave us a Ka value, but we're dealing with OH. So when we're dealing in the land of OH, what does this need to be?
You gotta switch it to KB.
KB, right. So before we compare and before we figure out if we can ignore this X or not, we need to be in the right value to be able to compare that. Okay, so we've got to change this into KB. So see if you can get this value into KB. So what does KB equal? Over KA, right? So then you got to remember what KW equals. I have this written down. I don't. So now that that's 10 to the negative 11, I can ignore that X. Okay, because that's going to be way more, the order of magnitude for this is going to be way out of bounds. We don't need to worry about that X. It's going to be so negligible compared to this 0.3 that it's not even going to be funny. Okay, so then we can set up our equation. Our KB equals our HF times our OH minus divided by our F minus concentration. Plug and chug. I'm going to have X squared over 0.3. And we already had the KB value here. I guess I could sub that in at this point as well. So that would be 1.39 times 10 to the negative 11. Oops, that's my pH, sorry. I got ahead of myself. And it's not letting me erase, so we will just default to that. 5.69. Subtract that from 14, and I'm able to get my pH value. So spend a few minutes seeing if you can come up with the answer to exercise 22 and 23. All right, so did you remember to turn your KB into KA? Okay, good. And then once you got down to here, you were able to determine this is your H value. So this is going to be your pH once you take the negative log of that. So you don't have to subtract it from anything because you're already at pH. Good? All right. So then salts as weak acids are the next ones. And this one, we are going to be calculated pH of 0.01 molar AlCl3 solution. The Ka value is given here. We've got to figure out, okay, what's going to happen here? Well, our aluminum is going to go together with water. It's going to pull off some of those OHs to make, you know, the ALOH, and then it's going to leave behind your hydrogens. So keep that in mind when you're doing this. So this is going to be your Ka. That's going to work out for us. So we don't need to convert this to Kb because we're going to be using our hydrogen concentration. So we're set here with our Ka. All right, so when you get that done, check your answer here. I'll put up the answers in a second. I want to go run those copies off for those notes because that's what we're going to start in on tomorrow, and I want to make sure that you guys have the copies. Yeah?
Why is this a weak acid? Because doesn't it form HCl?
HCl?
Yeah, wouldn't it be?
Right. The H and but remember, okay, so let's talk about that. So what happens here is that it's going to, okay. So this here is Al3 plus, right? And this right here is Cl minus. Well, when this goes into water, right, this will still stay as ions. Okay, nothing's going to happen with those ions. It's going to stay that way because it won't hook up with this because that would be a strong acid. It ionizes into those components, right? Okay, but this guy here, the aluminum 3 plus, he's going to hook up with some water. He's going to take the hydroxide from this.
Oh, because it leaves the hydrogen.
And it's going to leave this behind. Okay? If it's leaving that behind, this won't hook up with it. Okay?
That makes sense.
So since that won't hook up with it, it's going to increase our hydrogen ion concentration in that solution, which will then lead to our pH being altered. Does that make sense? What happens there? Okay, I'm going to go run those titration notes, and then I'll be back and put the rest of that up online. I'm going to just start that running off, and then I'll be right back, and then I'll go and pick up the packets when I'm done. All right, let's go back, see how that math flushes out, and then I'll go grab those copies. All right, so when we do this, we're starting out with 0.01 here, all right, and that's going to minus x. Over here, we are going to form x, and x will be left over, okay? This is 10 to the negative 5. It's good enough that we can ignore the x, document that, and move on. So 1.4 times 10 to the minus 5 equals x squared over 0.01. When I calculate for x, that's going to equal my hydrogen concentration. And when I do that, I end up with 3.74 times 10 to the minus 4. Take the negative log of that, and I end up with my pH. Easy? Okay. So I have another packet for you guys to work on. I shared that with the other group the other day. You can start working on that. I will put what page I want you to be through in that, and finish up the other packet here in just a few minutes. And I'm just going to stop